Welcome to Easy BTech, your guide for BTech and beyond. In the today's class, we will discuss diode switching times. How the diode can act as a on switch and how the diode can act as a off switch, and what is the diode switching times. How the diode switching time can vary. What is the total time period of a diode? That all we will discuss here. Okay, students, we will start the session. Diode switching. Okay, we know that diode is on switch. Diode is on switch during forward bias. Next, diode is off switch during reverse bias. These are the basic switching. Now, diode switching speed. Diode switching speed. Diode switching speed mainly depends upon forward and reverse recovery time. Okay, students, listen here. Diode switching speed mainly depends upon forward and reverse recovery time. Now we can understand what is forward recovery time. Forward recovery time. Okay, what is forward recovery time? The diode state from off to on state. Forward recovery time means the minimum time taken, or we will define in this minimum time taken to move its state from off to on. The minimum time taken by a diode to move its state from off to on state is known as forward recovery time. What is forward recovery time? Means from off state to on state, what is the time taken, you will call as a forward recovery time. Similarly, reverse recovery time. The minimum time taken by a diode by a diode to move from on state to off state, on state to off state, from on state to off state. The minimum time taken by a diode to move from on state to off state is known as reverse recovery time. Denoted by TRR, reverse recovery time. And forward recovery time is denoted by TFR. Therefore, TFR is forward recovery time is less than that of TRR. Okay. Forward recovery time is less than reverse recovery time. That is why the total switching speed is mainly depends upon reverse recovery time only. The total switching speed is mainly depends upon TRR because the time taking is more. Okay, the total switching speed, the total switching speed of diode is mainly depends upon TRR. TRR means reverse recovery time only. Is it clear? That is moving from on state to off state. Means making a diode off state from on. This time is TRR. Is it clear? That is why the total speed on to off means propagation. On to off, off to on. The switching speed is moreover, it depends upon reverse recovery time. Or to move from on to off, it takes a larger time. Okay. Therefore, TRR is nothing but TS plus TT. Okay. TRR is nothing but the two time periods are there, where TS is nothing but storage time, and TT means transition time. Okay, now it is suppose you can take a diode. This is a diode. Applied input voltage, you are applying input voltage, it is a diode. Now what happens when your positive cycle, diode is forward bias, okay, then it is on state. When during a negative half cycle, diode is reverse bias. Due to applying input, the switching speed can be differ from positive to negative, we can see here. Okay, during positive half cycle, due to positive half cycle, or due to positive half cycle, diode starts conduction. It moves from off to on state. Very less time period. Okay, now here you can see this time we will call as a from this time to this time, we will call it as a TFR. From here to this state we will call as a storage time. And from this state to this state, this time we will call as a transition time. From here to here we will call as a TRR, reverse recovery time. You can see storage time. Okay, now you can see now diode is there. During forward bias, what happens? During forward bias, holes from P side enters into N side. Electrons from N side enters into P side. Now this is what the actual action happens in the forward bias. Okay, now suddenly if you change the state, if you change the state, what happens? It means applying a reverse. Changing the state means apply a reverse bias. Applying a reverse bias across the diode. Across the diode. It never becomes to off state. It never becomes to off state immediately. It never becomes to off state immediately. Now you can see what action can be happens. It is a junction. Okay, what you can see here. Now it is a P side. it is a P side, it is an N side. Due to this forward bias, what happens? N side, here to here, what charges are moving? Holes are moving. These holes across the junction here, majority carriers. This is a path. It will move in this manner. It means exponentially decaying form. During the forward bias, holes from P side enters into the N side across the junction, maximum density. Across the junction, maximum density. But when it is moving, this minority carrier, because holes in N side are the minority carriers, when they are moving into N side deeper, then automatically what happens? It moves into the deeper, but its concentration is decreases across the junction more, and when it is moving the deeper, the path of traveling of an minority carrier in N side is in this manner. These all are electrons, and here also the same in this manner, the minority carrier. This is also negative. What are the minority carriers in N side, P side? In P side, holes are the majority, electrons are the minority. That is electrons in P side. Here means in P side electrons. Here holes in N side. Holes in N side. These are minority carriers. The formula from the mass action law, we will write NP is equal to Ni square by Na. And here we will write a Pn. Pn is equal to Ni, intrinsic carrier concentration by donor concentration. The minority carrier concentration. Now this is what actually happens. This is a This is what actually happens. You can see here, when you are applying when the diode is operated in forward bias, due to forward bias, this minority from P side majority charge carriers crosses the junction, and they will become minority carriers in opposite direction, opposite terminal. Now here in P, holes are majority, but when they are entering into the N side, they will become minority, and their concentration in N-type material are in this manner, exponentially decaying form. And in this electrons from N side crosses the junction, enter into the P side, and this. Now this is under forward bias condition. Now if you want to apply a suddenly, okay, if you change the state, applying a reverse bias across the diode suddenly, these all the charges must be become the zero. It means when in this state, when you apply a reverse bias, whatever the minority carriers are presented in N side, whatever the minority carriers presented in P side, they has to crosses and moves to its original position. It means the injected charge carriers become zero. Okay. Storage time, I can define what is the storage time. Storage time. The injected charge carriers, the injected charges are inducted charge carriers, the injected charge carriers across the junction will become 0, 0. That particular time is known as storage time. It means the time taken by a diode, whatever the injected charge carriers during the forward bias, that minority charge carriers must be becomes 0. It means no holes can presented in N side and no electrons will present in P side. The resultant must be 0. The time taken by a diode, the injected charges sum must be equal to 0. That particular time is known as a storage time. I hope you understood. Next, transition time. During the reverse bias, what happens? The exponential decreasing of current in the diode during the reverse bias. Is known as transition time. Now the total time, that is TRR is equal to TS plus T. This is the diagram. This is for on state. This time we call TFR. This time, from this time to this time, we will call TS. From here, it is this time. From here to here, TRR. Is the switching speed of the diode. Okay, students, these are the switching speed of the diode lecture. I hope you understood.